Today we answer the second part of that one-part question that 11.3 answered, like the first half. The question was, can we multiply vectors? We know we can add them, we know we can subtract them, and we know kind of that we can multiply them with this thing called that's right. The second half of the answer can we multiply them is yes we can. One way, dot product. The other way, a different type of product is called the cross product. Now, what the cross product is, you're going to find out. And it's actually the cross product makes a lot more sense just in what it is. When we do the computation, dot product was like, okay, we get this number, what's the number? And we spent an entire class discussing what that number was and how we use that number. Cross product, when you see what it does, it's going to be like, okay, I get it. I understand what this is. It makes something actually graphable, relevant that you're going to get. Before we get on into how to actually compute the cross product of two vectors, I gotta talk about determinants. Do you know how to find? I'm not going to get into like the nitty gritty of it, but do you know how to find the determinant of a matrix? Do you know how to do that? If you do, great. If not, it's very easy. You just got to remember the order. How we find the determinant of a matrix. Someone out there who knows, tell me how you would do it. This first.
Yes.
So we do a diagonal multiplied. Hey, that's where we get the product. Diagonal multiplied. And then plus, minus. Which one?
Minus.
This way?
No, B1.
This no, I'm telling you. I'm telling you this time. Yes. This way. And then a minus sign, and then this way. That's how a determinant works for a 2x2 matrix. Now, when we start the 3x3 matrix, which is where we're going to live in this class, there's a variety of ways to do it. I'm going to give you the best way to do it for working with vectors, right? So there's a couple ways you can do it. This one's going to work really, really nice for the stuff that we're going to use. Does that make sense to you? So you're like, I know a different way to multiply a determinant. That's great for you. That's awesome. Use this way, and you'll see why as soon as we start figuring out what the cross product is. Okay. There's a really unique thing that we can do. If you have a 3x3 matrix, we can actually take three 2x2 matrices, find the determinant of those, and multiply by those terms, those components, and get a determinant of a 3x3 matrix. I'm going to show you how it works. So if we do this is all going to look very confusing right now because there's been lots of numbers and letters floating around. It's honestly really, really easy to do, so don't let all the numbers and stuff confuse you yet. All right? What sign is that? For real, all right? Want to make sure that your notes are correct, that you have this, and I'm going to show you the easy way to actually go about doing it, all right? Because right now that looks really like, why would anyone ever choose to do that ever? But it's really easy. Firstly, do you have all the correct letters and all the correct spots? Do you have that down? I'm going to give you a second. Check your notes. Check this. Make sure you get a minus. Make sure you get a plus. Make sure it goes A1, A2, A3, and all these numbers are exactly the same. And then we'll show you how it works. All right? You guys ready for it? So the way to actually go about doing this, here's the way. If you want to calculate this first number, the idea is cover up the column. This works all the time, okay? Cover up the column that has that number in it. So cover up the columns go this way. Cover up that column. What that leaves you with is this matrix. Do you see it? Find the determinant of this matrix and then multiply by that top number that you just covered up, and that does it for you. Does that make sense? Cover up this column. Boom. Do you see the matrix that we create there? Same numbers. And multiply by the top number that you just covered up. Cover up that column. Boom. We got the same matrix. And then multiply by the top number that you just covered up. That is a very fast way to find the determinant of a 3 by 3 matrix. Very, very fast. The only thing you got to worry about is minus, plus. That's a big deal. Show of hands feel okay with the idea. We're going to practice it. It goes very fast. I will warn you, and it's going to happen to you. Because it happens to me, too. The biggest mistakes you're going to make, what do you think? Sign errors. Happen all the time. Especially when you got positives and negatives floating around, you're subtracting negatives. It happens all the time. Now we're ready. Oh, gosh. Get the chills a little bit. Did you feel that? It's like, oh, we're ready for something cool. That's what it meant. It's like the chills because it's so cool. You just get the chill. We're going to talk about what the cross product is now. With any two vectors, we could do a dot product. We can also now do a cross product, and here's what it looks like. Since it's still a product, it's got to have a symbol for multiplication, but we already used up the little dot because that was called dot product. But then we had this old symbol going like way back. What's the other one that we use for multiplication? Yeah, that's that little cross. That's called a cross product. What's really kind of convenient, not mathy, okay, is the way you find a determinant here is going across the determinant, which is kind of convenient. So cross product, cross the determinant, works for me. That's the way that we write the cross product. So whenever you see that, we're talking about a cross product. Are you with me what I'm talking about? I'm going to give you the definition of what the cross product actually is. I'm going to show you why in the world we have this thing. Because like, what? Why? And I'm going to put them together for you. Here's the definition of what a cross product actually does. So provided we have these two vectors, A1, A2, A3, and then B1, B2, B3, here's what the cross product does. Takes A2, B3 minus A3, B2, and puts an I after them. A3B1 minus A1B3, then puts a J after them. And then A1B2, A2B1, and puts a K after it. Here's my first question to you. When you did the dot product, what did it give you? Scalar. When you do a cross product, what's it going to give you? That's a different result. So this thing that we get, first thing, the cross product gives you a vector. By the way, did you make sure to put a plus there? I'm not making a mistake. Okay, put a plus there. I'll talk about why in a second. So first know, you got to know, this thing gives you a vector. Not a scalar. You know, let's even write that down, because a lot of people go, oh, dot product, cross product, what's the difference? Well, there's a big difference, but that's a huge difference between them. One of them is a scalar. We learned how to use it a lot last section. This section goes, okay, we're getting a vector. What's that vector do? That's the whole subject matter of this next section, okay, is what we're going to learn, is what it does. The main things you need to know right now is, firstly, how you do it this way. Secondly, what it is. It's a vector. It's for sure not a scalar. Now, the other thing, why we even did this. Look, you can do this for the cross product every single time. A lot of teachers teach it that way. Like, oh, that's how you do the cross product. You just take your vectors and you do the A2 with the B3 minus the A3 with the B2, and then you keep going and you do all that, and that's fine. It works every time. However, there's a really much more better way to do this. Let me show you that. So if I wanted to find another way to do this, check this out. This is pretty cool. If we take the components of our vectors, like that, and we put them on the second and third row respectively, and you're going to ask me this later, does the order matter? We're going to determine that, okay? Right now, put them in the order that I'm telling you, and we're going to see later, does the order matter? What's the order mean? What's the interpretation of that? Just hang on for a second on that one. And then up here we go, let's kind of do something really cool. Let's dot, or let's not dot this, let's put another vector I, J, and K, and let's see what happens. If we do it, I'm gonna have to bless you. I'm gonna have to bless you. I'm gonna have to bless you all. Now it's my turn. You have to bless me. Thank you. Let's now take this junk, apply it to this thing, and let's see what happens with it. Okay? So check this out. If I do this to this, what's the first thing I would do? This guy. Remember covering it up? I literally have to cover it up, otherwise I get my numbers mixed up, for real. So I cover it up, and I go, okay, it's this square matrix. Sorry, I'm doing the multiplication in my head right now. Now here's the magic. What goes there? Is it okay to multiply that's going to be a scalar, because these are all numbers. Is it okay to multiply a scalar by a vector?
Yes.
Absolutely. You're growing the I unit. That's what's happening. It's a unit vector, you're multiplying by numbers, just growing that direction. That's all that's happening. Hey, big one. Minus. It's a minus. Now, this is where you're going to be lost for just half a second. Oh, wait a minute. Just wait. You'll see. Trust the Leonard. Trust the Leonard. Just on this, though. Nothing else. Don't take financial advice from me. Life advice is big no-no. But trust me on the math. You can do that. I'm going to cover up the middle one now. Because, you know why? We go IJK. That's what we do. We're going to cover up that one. We have another square matrix. We have this, that. Again, scalar, vector, we're cool. Plus sign, just like we had. And if we cover up that last column, we got our last little square matrix here. And all I want to do right now, let's just verify they're the same, all right? This is no better or no worse. What this does, it gives you a way to remember it so that you don't have to memorize that, because that's a bunch of junk, man. It's hard to memorize. But memorizing this determinant, this determinant, this determinant, that's pretty easy, as long as you know about the minus. Now let's see if it actually works. If you did the determinant, come on, stick with me here. What numbers would you multiply?
A2, B3.
Minus?
Minus A2, B2.
Boom, boom, I. Done. Now wait a second. Why this difference? Let's do it. If we multiply, what would you multiply here?
A1, B3. Minus.
That's there. Minus A3, B1. That's there. They're out of order. That's the reason why we have the minus. So these things, when I do them, it's A1, B3, A3, B1. Do you get it? If I factor out, and that's reverse order there, but if I factor out the negative, then I get what I want. That's why we changed the plus to a minus, because they're out of order, because the determinant puts them out of order. That's why. Does that make sense? Last one's pretty easy. Last one says, yeah, hey, A1, B2 minus A2, B1, K, and that one works just fine. So that's why we get that minus right there, is because the nature of that determinant. Should guys feel okay with the idea behind
If
it?
you're factoring this for negative, you still have a negative on the inside?
Just like we had there. We're trying to make the determinant, this, match up with that one. To make it match, you have to factor out that negative. And when you do that, that plus becomes that minus. That's
Do we
why
have
we
to
have.
match it?
So, no, you don't have to do anything. What I'm telling you is that these things are equivalent, because when we put the minus there, it automatically makes the reverse order fit. You don't have to do anything. Don't factor nothing. I'm proving it for you. I didn't make it make sense. I can tell by the looks on your faces. Okay, so you go, okay, watch. I'm going to spring on the minus, okay? I'm going to do the determinant. That's literally what we have right now, right? But you go, wait a minute. Is this the same as this? The answer is, well, yes. And I can prove it by doing this. If I reverse the order and factor a negative, here's still the minus. Here's the factored negative. This would change to a, let's see, that would change to a negative. This would change to a positive. If you want to just distribute this, am I confusing the heck out of you?
No.
Yeah.
They're the same.
Got it.
But what is it? What is this? What is that?
Vector.
Yeah, that's a vector. That's great. What does that vector? What's it? Well, okay. You know what? Let's write them all down. So what is this? Number one. It's a vector. Hey, that's a big deal. You're getting a vector out of this. It's not a scalar. It's a vector. Okay. What's the vector do? This is the important part. What this creates, and this is the awesome part. A cross B, that's how you say it, by the way, just A cross B. It's obviously a vector. It's a vector that is orthogonal to both A and B. That's what this vector does. So if you have a vector A and you have a vector B, we have a vector that's orthogonal to both. Where they meet goes right through my head. My neck bone is connected to the shoulder bones, which are pointed like this, right? If I think of a vector that's orthogonal to both of these guys, it would go right this way. How about this? The z-axis is orthogonal to both the x and the y-axis, correct? If you cross I and j, you're going to get k. I cross j is going to give you a k, the vector that's orthogonal to both. That is going to happen. So A cross B is a vector that is orthogonal to both A and B. But wait a minute. What would B cross A be then?
Different.
Same or different? What do you think? Is it still going to give you, well, we have a definition right here. I'm going to prove it in just a bit. A cross B, it's a vector. It's orthogonal to both of them, right?
Yes.
So which means a I and J gives you K. That's if we went from I to J. What if we go J and I? Is it still going to give you K?
Yes.
Yes and no. Does it still have to be a vector that's orthogonal to both of them? It does, because that's what a cross product gives you. Is it in the same direction? That's what it does. So if I reverse the order, it's no longer positive k, it's just negative k. It still has to give you a vector orthogonal to both, but it's in the opposite direction. Does that make sense? That's kind of cool. this is also a vector orthogonal to both A and B. If they're the same, if they're both orthogonal, but they're not the same, you can't be like both be orthogonal to the same two vectors and not be going in the same direction, not have the same unit vector. So they're the same size vector even. They're the same vector, but in opposite directions. So they're not the same vector. But one is just negative of the other. That's what happens here. And that's the last thing we're going to write. So A cross B and B cross A, they're the same size vector, but they're in opposite directions. I'm going to say it this way because I'm saying the same thing. Here you go. Hopefully you see the same thing. I said that A cross B and B cross A are the same size vector, but they're just in opposite directions in mathy ways. We say that like that. One is just negative of the other because that all that does is flips the direction. It doesn't change the magnitude. It doesn't change the fact they're both orthogonal. Show of hands if you're okay with the idea. I'd like to draw you a picture to make sure that you really, really do get it. I'm going to do it right here. So let's say that's vector A and that's vector B, and there's obviously an angle between those vectors. Here's a couple things I need you to know. Firstly, the representation of what A cross B and B cross A means. What I want you to do, just imagine this right now. I'm gonna actually do it. If we are talking about A cross B, what that means is we're gonna put our hand with the palm side towards the vector we're crossing. So put your hand like it's on A, with your palm side open towards the B. Does that make sense? Seriously, do it. You're looking at me like I'm an idiot right now. Seriously, try. So it's like this. Now, close. So you don't have a thumb right now, all right? Close your hand so that A starts going towards B. Does that make sense? If you do that, your thumb is pointing up. Do you see what I'm talking about? Where your thumb is pointing is where that cross product vector goes. It's called the right hand rule. So if we put our hand on A, palm open to the vector we're crossing, so A to B, my thumb is pointing upward, my thumb is pointing this way right now. This is perpendicular to both A and B. That is A cross B. Now you're like, well, wait a minute. How is B cross A any different? Well, do you guys have flexible shoulders? That's what I need to know right now. I don't. So here's how you have to do B cross A. You have to put your hand on B with your palm open towards A. Eh? No. Eh? Yes. This is on B, palm opens towards A. When I close that from B to A, my thumb is pointing downwards. That's where B cross A points. One more thing. The angle here, you can't go any past pi. Now your finger doesn't go, you can't close your hand past pi, okay? So, because you get there the way. You don't want to go past pi because it'd be easier to cross product across the smaller angle. Does that make sense to you? So we're never going to go past 180, never go past pi. So this is defined for that. I really want to know if I've explained this well enough for you guys to understand the concept behind it. There was a lot behind it. I could have just given this and say, that's cross product. But we talked about this, we talked about what determinants are. We have not done one yet. I understand, like if you're seeing this for the first time, you go, that looks like a whole lot of work. Please just let it stick with the dot product, man. That's easy. This is just as easy, I promise. It's not hard. We're going to do a couple examples in just a little bit. Do you want to see the proof of, you know what, I'm going to hold off on the proof. If you want the proof that this vector and this vector are perpendicular to both, I'm going to do that when we finish our examples. Right now I want to get to our examples. Does that make sense? So we're going to do this proof a little bit later. I won't leave you hanging. We're going to do that in a second. Well, like 2 hours, but it will be on there. So you're gonna have to look for it later. And even remind me, because I'm gonna forget. You're not gonna remind me, are you?
No.
Thanks, guys. Thanks a lot. You know, test question?
Sure, yeah.
Almost guaranteed. Here's the test question. I want you to find two vectors that are orthogonal to both u and v. Write it down, then look up here so I know you all have written it down. I can talk at you, okay? So we got u, we got v, make sure you're writing it correctly. We want to find two vectors that are orthogonal to both of them. Okay, rapid recap. What's a dot product give you? Vector, scalar.
Scalar.
What's cross product give you?
Vector.
Vector that is
Orthogonal.
two,
And. Or.
whatever two vectors I give you.
Yes.
So when I ask you, find a vector that is orthogonal to two vectors, what am I really asking you? To the cross product. That's all I'm asking you. So whenever we do the cross product, we are finding a vector that is just orthogonal to both the given vectors. So let's try that. Let's find a vector that's orthogonal to both u and v. Let's find one of them and then go from there. Does that make sense? Let's find one of them. So let's cross u and v. Here's the way you set this up. The order does matter. I said hang on to that question in your head until like right now. Here's why the order matters. If I do it in a different order, I get a different vector. Does that make sense? This is A cross B, this is B cross A. I get a different vector. Now in the grand scheme of things, does it really matter? Well, that answers the second part of our question. If I wanted you to find two different vectors that are both orthogonal to both of them, well, if I just switch the order, then u cross v is going to give us one, and v cross u is going to give us the other. Does that make sense to you? So I'm asking you to do two cross products right here. So we'll try it. The setup is real important, all right? The setup always works the same way. Always, always, always. We put ijk. That goes first because that's the order of our vectors. We put the u components first, and then below that we put the v components. Make sure you do not forget signs. Make sure you do not forget the order. Make sure you don't switch them up in your head accidentally. So for u, tell me the components. Everybody, real quick, what's the components?
-3, 1, -2.
That's it. You got it perfect. How about for v? Everybody, what is that?
1, 1.
We're going to show that we're making a determinant, and then a lot of this stuff, look, this is This is a way to do it. Don't write this. This is crazy. All right, don't do that. Don't write all that out. Don't write the determinants. It's just telling that you need to do the determinant. So literally, here's what you need to do. Cover up which one first? If you want the I, cover the I. If you want the J, cover the J. If you want the K, cover the K. We want to cover the I. We're left with this square matrices, okay? We're going to find the determinant. What two numbers would you multiply?
1 and 1.
What's 1 times 1?
1.
And then you subtract. Put the this is where you're going to screw this up. If you're going to screw anything up, it's going to be right here. It's going to be I promise it's going to be sign errors. Seriously, I've been doing this a while, all right? I still make sign errors unless I do this. I put 1, I put minus, and I put what the other one is. This right here, because your head is going to want to make you think -2. Trust me, it's going to want to do that. So write down at least those two numbers being multiplied. Can you guys do that? Do it for you. Don't do it for me. Do it for you. Save you a lot of headache. It'll save you a lot of time. I'm saving your life here, all right? Your life is time. I'm saving your life. Trust me. So 1 minus -2. You guys get what I'm talking about? That's all you got to show. And then what am I going to multiply that by? I. Yeah. And then we continue. There's a big part. You're going to forget it occasionally, but don't forget it all the time. All right, go back, and if you get the wrong answer all the time, you're probably forgetting this next thing. What goes right there? The minus. And it says, hey, if you want the j component of this new vector that's orthogonal to both u and v, cover up the j. What's the first number we're going to write down, please?
-3.
Minus. Minus what? -2. J. Let's make sure I got it right, because there's a lot going on. 1 minus -2. Got it. Minus sign, cool. -3 minus -2. Got it. J. What's the next one, a plus or a minus?
Plus.
If I want the K, I'm going to cover the column with the K in it. What do I write down?
-2.
Good. -3. Awesome. -1. Can you do it faster? Of course you can. I mean, you could do this all in your head if you really want to. And that's fine. I'm just I'm giving you a tool here. When you do, more mistakes happen. And you know this because you've been in math a long time. You know the more that I start working with stuff in my head, the more sign errors I'm going to make. So now work down nice and slow. Honestly, I've told people in the past, just pull out a calculator, just plug in 1 minus -2. Just do that. That way you don't make any errors. If you're good at it, cool. This is how much? This is how much? -1. It's easy to make mistakes, isn't it? It's easy to get that just slightly jacked up. And then this? It's not 4K, it's minus 4K. Did you already make some mistakes?
Yeah, the J.
Happens all the time. Hey, why don't you guys take a calculator out and just kind of put the numbers in? Trust me, for real. Because the last thing you want to do on a test, or anytime you're doing homework, really is fully understand a concept and give me like 5. Right? Because that can happen really fast. That's -3 plus 2. That's -1, and we're subtracting negative. That's plus 1. And now if you're okay with that one. Now, what is it? Don't just do math for the sake of math. That's how people fail classes. What is that? What's that thing? It's a vector. Very good. Yeah, and it's a vector that's what? So if I have u and v, this vector's going this way. Verify that for me. How can you find another one of those vectors that's orthogonal, mutually orthogonal to both u and v? What would you do? Do it. Do it. See if you can do it. I'm going to give you about 2 minutes. I'm going to erase the board, see that you can do u cross v. Man, let's make no mistakes on it, all right? Let's try that. Is this stuff cool to you at all? Is this kind of a little bit cool? Just a little bit?
That's the
Yeah.
coolest thing I've seen all day.
Awesome. I love hearing that. Coolest thing I've seen all day. It's the coolest thing I've done all day. I was stuck teaching Calc 1 for 4 hours. I do like Calc 1 though. It's kind of fun.
What is Calc 4 all about? What's up with that?
We don't even have a Calc 4. We just stop. All right. Just forget about it, dude. Just forget about it. Quarter systems usually have Calc 4. Usually they break it up a little different, and then they'll have differential equations. We do Calc 3 and differential equations. That's how it goes. Some people consider differential equations to be Calc 4. Kind of is. If you're done with that already, or if you're a good thinker, then you're already done with that. Try this one on your own. By the way, did you have enough time to actually do this? Can you focus up here for just a second? Okay, stop what you're doing. Did you do the whole matrix thing and do all that stuff?
Yes.
Yeah. Wasn't.
Tell you what, did you look at your answer?
Yes.
Yeah.
Did you look at this answer?
Yeah.
Now answer me this question. How do you find a vector that's the same length, but just in the opposite direction? What do you do?
Multiply by negative.
I gave you a property up here, right? I told you that this is that. Same thing. So if I want to find B cross U, this is your understanding of the property, okay? The idea of a cross product says, hey, this thing, they do the same thing. It's just in opposite directions. If I want opposite directions, same length, all I got to do is multiply by a negative. It switches the direction. So if I ever ask you for two vectors that are like orthogonal to both, you just got to find one and then switch the sign. So right here we'd say, yep, this is going to be, I guarantee it's going to be negative 3i minus j plus 4k. I want to know if you guys found that one. Either way, show of hands if you did, you found that one. Good for you, that's fantastic. So next time you get the question, do you have to do both matrices?
No.
Now, I wanted you to get the practice on it to make sure you got it, but in the future, you gotta just find one, and then you can switch that sign around and find the other one. Try that on this one. I'll give you a couple of the minutes. I want to find two unit vectors. What I want is for you to at least find the vector that is orthogonal to both. And then you can stop there. We'll talk about the unit part. It should be in your head. See if you can complete it. We'll do that in a second. How far are you at? Have you set up the matrix yet? It's going to let you solve that. Have you found the cross product of these things? Good. When we're asking for a vector that's perpendicular, orthogonal, normal to two other vectors, we are asking for a cross product. That's all we're asking for. Does the order matter? Does the order matter in which? Are you going to get the same answer if you switch it around?
Yes.
Yeah. Well, opposite.
You're not going to get the same answer, but you will answer this question no matter which way you do it, because if you're looking for both of them, the reverse order of a cross product is what gives you both of those vectors that are mutually orthogonal to both A and B. So if we set it up, I'm going to do A cross B. I'm really careful not to forget any signs. I want to be pretty organized in my work. I also don't want to do a whole lot of shortcuts because I know myself. I know I'm going to make some mistakes on signs if I do. So the way we do it, we go, okay, double check, -1, 1, -1, 0, 3, 4. We got that. We got I, J, and K. So when we're doing this, we're going to cover up the I column. We have 4 minus -3I. Did you get that? Next thing is what? Come on, everybody, quickly. Oh, that was like one person. What's the next thing in this method? What do you do?
Minus negative.
-4 minus? 0. I love that. I love zeros. Plus, you're noticing I'm not doing a whole lot of work in my head. Honestly, for real. It's really easy to make mistakes. Hopefully I'm right. I want you guys to double check my work all the time when we're doing this. Did you get the same thing I'm getting? Okay, so let's complete it. A cross B, 7I, 4J, minus 3K. Did you get the same thing I got?
Yeah.
Now here's my question to you all. We gotta think back. Did you answer the question?
No.
No. What was the question?
Unit vector.
Is that a unit vector?
No.
Okay, so what is it? Come on, put it together. What do we have?
A vector.
It's a vector that is
Orthogonal.
to
A.
both of them. That's great. That's like halfway there. So we've just got one vector that's orthogonal to both of those, but it's not a unit vector. Come on, everyone in class right now. How do you go from here to a unit vector? Quickly.
Divided by magnitude.
Great. So as long as we have that vector that's orthogonal to both, and we can find a magnitude, we can find a unit vector. A unit vector is always vector divided by magnitude. So if you haven't done it already, we're going to do it now. The magnitude of A cross B, pretty easy to find. 49, 16, 9. We take the squares, add them, square root them. Never a negative in there, it doesn't even matter. Sure. Double check, 74? Perfect. What do we do with that? Unit vectors are always the vector itself. We have that. Divided by the magnitude. Takes the length, divides by the magnitude, changes into a length of 1, the same direction. That's why we say unit vectors are direction. So what we're doing here, we're finding the vector that has the direction of the perpendicular. That's what we're doing. Why do we do all this stuff? We're going to talk about planes in the next section. Not this other planes. That'd be awesome. But like planes. And we need normals to do it. We need orthogonals to do it. We need cross product to even do it. So if we can't find an orthogonal, we can't even talk about planes. Did you get the idea? We're gonna do that. So for us right now, honestly, I put it like this. I leave my vector, this is A cross B. We know that when we divide by the magnitude, it's like having 1 over the square root of 74. This is the same. Is that making sense to you?
Yes.
Same. It's like dividing, but you have 1 over that. You're probably not going to see that, though. What are they going to do to you?
Root 74.
They're probably going to rationalize. Would I distribute it? Not unless I absolutely had to. A lot of times unit vectors are really nice when you leave that nastiness out front. That's what I'm looking for. Have we answered the question?
No.
Okay, so now, do we have to redo all of this work if we want to answer the question?
No.
This is, okay, let's follow through. Is this orthogonal to both A and B?
Yes.
That's what cross product does. Is it a unit vector orthogonal to both A and B? Is it two orthogonal vectors to both A and B?
No.
What's the other one?
Negative.
Put it, so this is one of them, and another one of them. Yep, negative reverses the direction, keeps the same magnitude. It's all good. Well, we've already done a lot of work. I'm going to deal with one more thing before our little break here. I'll leave you with a punchline to think of for the 10 minutes that we have our break. It's going to be pretty cool. It's going to be pretty freaking cool. All right, so you stick with me on this one. Do you remember what this equals?
The vector times, or the dot product.
The dot. So the dot of v dot v. That's what it does. Do you recall that little thing that we did? Stick with me here. We're gonna have something pretty awesome. We're gonna go a little bit past because we're kind of rolling here, and I want to get this proof done so that you and we're doing this proof for like the rest of this section. It's pretty cool. Well, not the whole proof, but the corollaries of the proof. Well, let's look what happens when I take the magnitude of a cross product and I square it. By this definition, I get the magnitude of a vector. Verify that's a vector. Come on, vector. Which means that I can take this vector and say this is equal to the vector dotted with itself. Can you actually do that? Yeah. It looks really nasty, all right? So for the rest, I really don't want to do all the algebra. Please don't make me. Please? 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 Okay, I'm not going to anyway. So for real, all right? But you could do it. You could do it. You could set up IJK, A1, A2, A3, B1, B2, B3, figure out both of those things, dot product them, which means multiply each of those components together, do like some crazy factoring, and then what we get after all of that stuff, which I have on my paper, it's like this, all right? What we get is this. So lots of algebra, trust me. That A1, A2, A3 all squared added. Oh my gosh. Does that look familiar to you? Freaking should. Come on. Does it look familiar? Should. B1, B2, B3 all squared added. And then we get this A1, B1, A2, B2, A3, B3, and we're going to see what that is. But these ones should look pretty familiar. In fact, what this should look like is the inside of a magnitude. Does it look like the inside of a magnitude? Or if it's the inside of a magnitude, that's the same thing as the magnitude squared. That's literally how we got, let's see, that right there. That was one of those properties. That this. Those are all equal. It was in a previous section. But that is the same thing as a magnitude squared. Question
First
first.
one times the second one minus the third one?
Minus.
Okay.
Well, let's keep on rolling. Come on. Hey, what's this one then? You don't have to whisper.
Square.
Good. If it wasn't squared, it would have to have a square root. Did you guys get it? This one, I'm going to do it this way. You're going to have to just verify that this is true. But if you really look, if you're good at dot product, you can see what this is. This is the x components multiplied, the y components multiplied, the z components multiplied, and then added. That's a dot product, squared. This is the dot product of A and B. Try it if you don't believe me. A1 times B1, and then A2 times B2, and then A3 times B3, and you add them up. That's what that is. Y'all still okay with it? Now we're doing some crazy stuff. If you don't want to write down only the punchline, that's fine too. I don't really care. I just want you to understand where this comes from, because if I just give you the formula, you know, where's that come from? I want to show you. One more thing, and oh man, I swear we're almost there. Do you recall that one of the ways we could do a dot product was that?
Yeah.
Do you recall that? We had magnitude times the cosine angle between them. And what we have here if this is now A and B, then we have, please just watch careful, we'd be squaring both sides of that to get down to here. Does that make sense to you? Are you sure? So VW is magnitude V, magnitude W, cosine between them. A dot B squared would be, you tell me, left-siders, what would you have? Okay, right-siders, what would you have?
Magnitude A.
Magnitude A.
Times the magnitude of B times cosine theta.
You're very, very close.
Everything's
This would
squared,
be exactly like this, but this is being squared. What's the square do to all this stuff?
Squared.
Because it's all being multiplied, I can say that square is applied here, it's applied here, and it's applied there. Okay, still following what I'm talking about. I know we're doing a lot of algebra, but I hope that you're with me. Head nod if you are. Still okay. You guys ready for the rest? It's pretty cool. Check this out. How many big terms do we have here? Terms are things added or subtracted. How many terms do we got? Two big fat terms. Do any of those terms have something in common in there? You know, let's factor it. F word. You know. Oh no, that's fraction. What? No, that's not a thing. That doesn't happen. We don't get stuff like that. Come on, you're in Calc 3. What is that?
Sine
squared.
That's cool. That's pretty cool. Now, yeah, I don't see the coolness yet. Don't worry about it. It's going to get chilly. What we started with was the magnitude of the cross product squared. That's what we started with. That's what this whole thing is equal to. Are you getting what I'm talking about? Everybody in class right now, how do you get rid of a square? How do you do that?
Square.
Can you square root both sides?
Yes.
Absolutely. You can. Magnitudes, always positive. Magnitudes, always positive. Magnitudes, always positive. I don't have to worry about the plus or minus thing because they're always positive. This guy we're going to talk about in a little bit. But if I square root both sides, if you're wondering if that's legal, why sine stays positive, I don't have the plus or minus, I need you to think back to the definition that was right over here. Do you remember that for a cross, you remember.
0 to pi.
It is 0 to pi. So for cross products, little sub note, okay? For cross products, theta is between 0 and pi. Tell me something about sine for any angle between 0 and pi.
Always positive.
It's always positive. So when I take the square root, it's an always positive number. I don't have to worry about the negatives. Which means when I take that square root, we're all good to go. You still okay with what we're doing so far? We're almost done, I swear. It's been a lot of proof. But it's the cool part. It's the cool part. You believe this, right? Because I proved it. Oh, it's the cool part. Now here's the deal. What we know is that any vector in the world can be written like this. The magnitude of the vector times the direction of the vector. Vectors are magnitude times direction. So it can be written as magnitude v times a unit vector of the direction of v. Are you with me on what I'm talking about? Okay, so wait a minute. Is A cross B a vector?
Yeah.
Then A cross B can be written as the magnitude of the vector times the direction of the vector. Magnitude times direction. But wait, we got a formula for that now. The reason why I'm doing this is it's going to become apparent in just a second. But do you guys see a similarity here? Do you remember the dot product? We had it earlier. The dot product of A and B was that thing. Do you remember that? The dot product, that's really similar. We just have the sine versus the cosine. Now this gives us a scalar, this gives us a vector, but that holds the vector right there, just the u, just the direction. So that's pretty cool. This is the other way that you can calculate the cross product if you know the angle between the two vectors. And you can find the magnitudes, right? So if you know the angle between the two vectors and the magnitudes, you need to know the unit vector of the cross product. But that's another way that you can do it. Now, here's what I want to talk about. The big old punchline. So we got two ways now. We got this way for vectors with angles. So if you know theta, and we had this way. If you have component form. There's just a little bit more. I promise I promise this time. I really promise. I'm not even break my word. I promise we're almost done here. There's a big question. We know what happens. Oh, come on, stick with me here. What happens if a dot product is Siddle? What happens if the dot product is 0? We knew that, right? Think through it. If the dot product is 0, the only way that happens with non-zero vectors is when cosine is pi over 2. Tell me the angle of pi over 2. Come on, angle of pi over 2, what is that? If the dot product is 0, we have perpendicular. Are you following what I'm talking about? It's the one way we know. What happens if the cross product is 0? whole reason why we did this was so I can prove this little piece right here, but it's pretty neat. It's pretty cool. If the cross product is 0, this is the cross product. The only way that happens with a non-zero vector is if that's 0. That's the only way it happens. Do you guys see what I'm talking about? If the cross product is actually 0, and you have a non-zero vector, so it actually has some substance to it, the only way that happens is if this part is 0. So if the cross product is 0, it means this part has to be 0. But wait, if these vectors actually have length, these are not 0. It comes down to this. This can only happen, the cross product can only be 0 if sine is 0. Now you tell me, think about it, put it together. Where is sine 0?
0 and pi.
And remember that we can go from 0 to pi, but sine's 0. Sine's 0 only at 0 and pi. You follow me? Let's put it all back. Let's go backtrack. Hey, if sine is 0 or sine is pi, we're going to have 0 here. We're going to have a cross product of 0. This is the only time we ever get a cross product of 0 is if sine is 0 or pi. Tell me what two vectors are at 0 or at pi. What are those two vectors? They're parallel. That's the whole thing. What? It's pretty cool. So we have two pieces of information. One we just recapped, and you know it. You should know it. What happens if A dot B is 0? What do you know about A? Not about the angle, I mean about the vectors. What do you know about the relationship between the vectors? What do you know? They are orthogonal, they are perpendicular, they are normal. That's basically what we know. A and B are perpendicular. Does that make sense to you? We just talked about it. What do you know if you do the cross product and you get 0? Or what happens when you take vectors that are this situation and cross product them, you're going to get 0. What are those two vectors if the cross product is 0? They are parallel. And they have to be because the only way that happens is if sine is 0 or pi. Can I tell you something and you not get mad at me? You're still going to be mad at me, probably just a little bit. This is the only way you ever check whether vectors are perpendicular right here. Please don't freaking use this to check whether vectors are parallel, because still it's easier with scalar multiples, all right? We're going to use it, I promise we're going to use it for something called torque, but you still wouldn't use this to check whether vectors are parallel. Does that make sense? It's just a condition. It just happens. If the cross product is 0, you know the vectors are parallel. If the vectors are parallel, this is probably the more important case. If the vectors are parallel, you don't need to bother finding the cross product. That's why we're doing it. So if we know this, the cross product will be 0. Don't bother, because the angle's 0. Or pi, you're going to get a cross product of 0. Does that make sense?
Yeah.
So how do you check whether two vectors are parallel? What would you use?
Scalar
multiple. Still. How would you check whether vectors are perpendicular?
Dot product.
Yeah, still. That's where we're going to take our break. So, area. You're like, wait, what, does this actually do stuff? It does stuff. We're going to prove a couple things that it actually does right now. So, we're going to talk about area of a parallelogram, area of a triangle, volume of a prism. We will talk through some of the properties. We'll do one example illustrating those properties, and then we move on to torque, and I give you that proof that I said I was going to hang on to. Okay, so let's talk about area of a parallelogram. Very geometric idea, area of a parallelogram. And in fact, we know what area of like a rectangle is, and a parallelogram has the same exact formula for the area. It's simply base times height. It's just the height that's funny, because this is no longer the height. This is like, a diagonal. So area of a parallelogram is still base times height. Now, you people out there, if this is my parallelogram, what's the base? No, it's not u, because u's a vector, and u has a direction and a length. You can't be the base that we use for a computation, okay? Because it's a whole vector. So I'm going to ask you again, what's the base?
Magnitude.
Magnitude of u, that's right. So the length of u would be the base here. So for us, for this parallelogram, I'm going to call it a sub p, okay? A sub parallelogram. Would be base, sure. Times the height. Now, okay, wait a minute, the height. True or false, the height is the magnitude of v.
False.
No, the height has to go from here to here. Or in other words, if I drop this, if I drop that, the height would be the distance of that dotted line. That's what the height is. Now, if we have an angle right there, which we do, let's see. You guys know these things called right triangles, right? So right triangle says, hey, here's our angle. Here's I don't really care. I'm focused on these two sides. What's this side? As far as a right triangle is concerned,
Magnitude.
hypotenuse, and this side would be the adjacent to this one. This side would be the opposite. What relates the opposite to something that I already know, the hypotenuse? What relates that?
Sine.
Okay. So this right here, let's call that question mark just for a second. Sine theta is opposite over hypotenuse, correct? So it'd be question mark, whatever that happens to be, over what's this thing?
Magnitude.
Yeah, it's not v, it's just the magnitude of v, just that length, the length of that side. That's how trigonometry works, just lengths of sides. Do you guys get what I'm talking about? It's weird because we got a question mark, but I want to put the thing up here. So if I solve for a question mark, basically just multiply both sides by the magnitude of v, we got this side magnitude of v times sine theta. Do you guys have questions on this before we continue? Do you guys see the relationship I'm talking about? Opposite over hypotenuse. Just solve for the opposite. And we have that. Hey, do we have a base? Yeah. We got this whole base. Magnitude of u. Do we have a height now?
Yep.
What's the height?
Magnitude.
Huh. What's that?
Cross product.
Not quite the cross product. Not quite. Because the cross product has this. I don't have this. I have just this. I got just this piece right there. What was this piece?
Magnitude.
Vectors are magnitude times direction. Magnitude times direction. This piece is the magnitude of the cross product. Are you following what I'm talking about? This is the base. This is the height. The way that we can get this is the magnitude of the cross product of the two vectors that this angle's between. Since this angle's between u and v, this is the magnitude of the cross product of u and v. That's pretty interesting. So what's really cool is if I give you any two vectors and say, hey, there's only two vectors. Those vectors, you know this by the parallelogram law, makes up the parallelogram. So find the area of any parallelogram that's bordered by two vectors. It's easy. Cross product, magnitude, done. That gives you the area that's contained by the parallelogram bordered by these two vectors. It's pretty neat. That's pretty cool. You guys okay with the proof on that one? How about this? What's the area of the triangle that's bordered by these two vectors? Remember that triangles cut parallelograms like that. What would the area be for a triangle that's bordered by V and W?
One half.
Just half. Just like half base times height, it's half base times height. Did you expect that the cross product was going to have anything to do with the area of a parallelogram? It's kind of cool. It's really interesting. If you really think about it, kind of funny. Think about it this way. The cross product would give you a vector that's pointed straight at you. Does that make sense? The length of that vector is numerically equivalent to the area of that. Half the length of that vector is numerically equivalent to the area of that triangle. That's cool. That's really weird. And it all works out, and I just proved it to you. You guys want to try an example just to illustrate this? Before we go any further, I want to talk about some properties. You know one of them, and we're going to get to this example, but some properties that you can use with a lot of this stuff. Number one, the cross product is distributive across addition. So if I want to find the cross product, like A cross B plus C, you can do A cross B plus A cross C. A lot of the properties you expect are there. The only one is commutativity doesn't quite work, and you know it because we talked about it already. If I reverse the order, I get a negative sign because the orthogonal vectors are going in opposite directions. Other than that, when I cross product with a 0, I still get a 0. We have, with this one you should know, if I cross product A with A, if I cross product a vector with itself, what am I going to get? And then why? Cross product a vector with itself. What would you get? You would get what? 0. Why? Because a vector's parallel to itself. You have to get 0. That was only really the only surprising one that we have. That's pretty much it. I want to talk about this example, the area of a triangle, but that's not too bad as long as you know how to do the cross product. So let's put this together from one through an example. It should be pretty straightforward, and then we'll talk about volume of a prism. So we got this triangle, and I've given you the points of the triangle. So I want you to find the area of that triangle, where P is that, Q is that, and R is that. Write it down, look up here so I know you got it. Give me an answer here. Does the cross product work with points?
No.
See any points up there? What do you see up there?
Vector.
You see vectors. Can you find vectors from points?
Yes.
Yeah, so anytime I give you points, it's not a huge deal, but you do need to know how to find a position vector, which is why I'm going to give you a problem like this on a test, because it tests a lot of stuff in it. It says, hey, can you find a vector between P and Q? Yeah? Can you find a vector between P and R? Yeah, that's awesome. Can you find the area of that triangle? That's a cross product. Can you do a cross product? Yeah. Can you do a magnitude? Yeah. That includes all this stuff. Does that make sense to you? So when we have this triangle, you don't have to draw it. I don't care that you draw it. But you do have to do one thing. You got to start with what the vectors are that border that triangle. Basically, that border the parallelogram, then we're going to cut it in half. Okay, that's what's going on. My only advice to you is whenever you do this, please start with the same letter. Don't do PQ and then QR. Because when you do that cross product, it's going to be a little bit weird, okay? So when you start with this with one letter, keep starting with that same letter until you exhaust all the vectors. For instance, to find this, and it doesn't matter what letter you start with, just start with the same letter. So I would start with P, Q, and then the next vector I'm finding is what? PR, not QR, PR. I hope you understand why. The idea is these things, in order to find a cross product, they need to have the same initial point. So if I'm starting at P, I want to keep starting at P. That way when I do the cross product, they actually match up. Does that make sense? I don't want to start here and then start here. That doesn't make sense. It wouldn't give me the same, well, here and here. It wouldn't give me the same exact relationship there. So start with the same letter. That's about as much as I can say. I'm going to give you about 10 seconds. Find the position vectors for those. Whatever form you want to use is absolutely fine. Take some time when you do these, double check. It'd be the worst thing in the world to know how to do a cross product, right? To know what position vectors are, to get everything done. Like, oh man, I put 1, it was -1, and you get the whole thing wrong. Don't do that to yourself. So take some time. Did you get the same thing that I got? Yeah. Okay, so what we've done is we've found out this vector and this vector, and we're looking for the area of the triangle that those two vectors border. What's the next thing that you're doing once you have those two vectors with the same initial point? What would you do?
Dot product?
What gives you the area of a... Do you understand the question?
Yeah.
Find the area of a triangle. Triangles come from parallelograms. So let's find the area of a parallelogram and then cut it in half. Do you guys get that this is just like this vector, and this one's just like that vector? So how do I find the area of the parallelogram that these vectors border? Come on, we just did it. So let's find the cross product first, and then we'll find the magnitude. You can't do it all at once. You got to find the cross product first and then find the magnitude. Can you guys see what I'm talking about here? If it helps you and you're like, man, I don't know about PQ. If that doesn't work, well then call this one vector V and call this one vector U. I don't care what you call them. But at some point, you're going to have to do the cross product. In order to find the area of a parallelogram. Well, at least find it easy. Question to you, does the order matter? Does the order matter when you're doing this?
Yes.
I'm going to ask it again, and I want you to think about it. At the very end, when you do the cross product, you're going to be finding magnitude. Do negatives matter in magnitudes? So no matter how I do this cross product, you can't mess it up. Because if I get negatives, I'm squaring them anyway. If I get positives, I'm squaring them anyway. So I'm finding the magnitude of this thing. It doesn't matter the order. I'm just going to get a different vector, sure, but magnitude of that vector is going to be the same. That's the whole point here, is that these two different vectors have the same length, just different directions. So magnitude has to be the same. Hopefully, as I've been rambling, you've been working. We're at the point where I'm not going to be doing a whole lot of work on the board. I'm expecting that you can actually do it. If you've done it already, what's our I component after you've done this and this? So 8 minus -4. Hopefully you got 12i. Very good. Then we got 2 minus 3. There should be -1, but you have a minus there, so you have plus j. Did you get plus j?
Yep.
Okay, we got 4 minus -12. That's 4 plus 12. That's 16. Did you get 16k?
Yes.
Awesome. That's fantastic. Show of hands, feel okay with finding that. Perfect. Okay, stop right now. What is that? What is this thing? And don't just say it's a vector. What is this vector?
Cross product.
I know it's a cross product. We just did that cross product. What's it represent?
The area base.
You want to see a teacher cry? This is what makes a teacher drink at night. Do you know that? This is really vodka. I'm drinking right now. It's not. I promise. It's not. It's just water. Otherwise, I wouldn't be able to actually. I don't drink. Maybe a glass of wine, like once a month on an anniversary or something. You know, it's fun. What? Look at this. Is this an area? Is that an area?
No.
Can a vector possibly be a freaking area? Does it make sense? It makes sense. The magnitude of that vector, yes. But what does this vector represent? We just spent like an hour and a half talking about crossbar. What's that vector? What is that vector in relation to these two vectors? What is it?
Orthogonal.
It's orthogonal. So this is the vector that points out from the board like that. And it's at that point, because that's where we did it. Does that make sense to you? That's what that vector is. Now, because of this really neat math I just proved to you, when I find the magnitude of said vector, it also represents the area of the parallelogram. So let's find that. Let's find the magnitude of this. Oh, dang, I can't do that. Is it 256? I don't know. I guess I did know. Help me out. How much?
401.
401? True or false? We're done. Okay, what is this? What is it?
Area.
It's the area of...
Parallel.
Very good, because that's the parallelogram thing we just had right there. How do I answer the question the correct way? Area of a...
Triangle.
So the triangle is going to have an area of... Just put 1/2 in front of that thing and call it good. Or put it over 2, and that's the area of the triangle. Square root 401 over 2, and you can approximate it, and that's what I want you to know. Head nod if you feel okay with what I want you to know. So we've talked about the properties, we've done one example. I want to extend the concept just one time. We're going to talk about volume, and then we're going to be just about done with this section. We'll talk about torque and that one proof. Any comments, questions at all before we get going? No? Nothing. Making perfect sense? Do you know how to find a cross product?
Yes.
Do you know what it means?
Yes.
Do you know how to find a dot product?
Yes.
Do you know how to use it like 14 different ways?
No.
Do you know how to find the area of a parallelogram?
Yes.
Know how to find the angle between two vectors?
Yes.
What's that involve? Cross product or dot product?
Cross product. Perfect.
Area between two vectors. Actually, if you really solve for it, either. When you think about it, cross divided by that would give you, well, magnitude divided by the magnitude to give you sine. So pretty much either. But use the dot product, it's easier. Okay, so I told you I was going to give you volume. Let's talk about volume. Is that good enough for you? Did you get the picture? I'm not very good at it, so that's the best way I got. This right here is a really weird word. It's called a parallelepiped. Can you say that 3 times fast? Parallelepiped. Say that?
Parallelopiped.
You said python. Some of you guys said pythons. That'd be awesome, but it's not. Parallelepiped. Piped.
Piped.
Yeah, that's what this is. It's a parallelepiped. That's that. It's like a parallelogram in 3D. Okay, that's what we got here. So let's say that I'm going to use some different vectors. From this point, we got vector B. Got vector C. I'm going to remake it dotted. We got vector A. You guys okay with the picture? If we think about how you really find the volume of something, look, I know it's base times length times width times height. That's what volume generally is of a regular geometric figure. But you can also do it this way. You can do the surface area of the base times the height. Why would we want to do that? Why would we want to, instead of reinventing the wheel, why would we want to do the area of the base, surface area of the base times the height? What is the shape of the base? Do we know how to find the area of the parallelogram? So if the volume is the area of the base times the height, that's something we already got. Everybody, what's the area of the base, when the base is a parallelogram, what is it?
Magnitude.
It's a magnitude of...
Cross.
You are not as excited as you should be on this. This is pretty cool. We're putting everything together here. And you're going to see some neat stuff after this. What's the... What is it?
Magnitude.
It's a magnitude of a...
Cross.
Which two vectors would represent the parallelogram quickly? What is it?
B and C.
So this would be the magnitude of B cross C. Now the height. Height is interesting. The height, we're going to do something very similar to this over here. So here we go, okay, let's make a right triangle. Well, the height, I don't want it this way. I want the height as an angle off of the actual vertical height here. So if I do that, I'm going to make this a little smaller, but that just says A. If I stick something that is mutually orthogonal to both B and C, you hear my emphasis there, mutually orthogonal to both B and C, it's going to represent the height, at least the direction of the height. Does that make sense? So let's just do that. If A has an angle off of that, then really what the height is would be the projection of A onto that height. Just like we had the projection of B onto this height. Same idea. Only it's a different side relationship. Come on, you know, you've taken trigonometry. If I have an angle here, and this is my, what's that as far as a right triangle? Hypotenuse. What's this side? It's adjacent. What compares adjacent and hypotenuse to us?
Cosine.
So from here, this height, question mark if you will, cosine theta is always adjacent over hypotenuse. If the hypotenuse is the magnitude of that vector A, then when I solve for question mark, we get that. Okay. So this question, okay. So this question mark, the height, height is that. Awesome. What's it mean? I'll tell you. Firstly, let's look what this is. This is a vector or scalar. This just the inside. Magnitude gives us a
Scalar.
What's this? Vector or scalar? Come on.
Scalar.
What's this?
an A.
If they're all scalars, that means I can reorder them and be just fine. I'm going to do that. So what I'm going to do is reorder and put the A first. And man, we're gonna use this one more time, and then we're gonna have something pretty freaking awesome. Okay, check this out. You don't need to rewrite this; it's in your notes at least 5 times. It's there at least 5 times. You know that this equals that, correct? Please look at it carefully because I'm going to do it here. Look at it carefully. What this has, it has a magnitude of a vector. It has a magnitude of a vector and it has a cosine of the angle between them. That's what it has. You guys get what I'm talking about? And it equals a dot product of this vector, the first one, with the second vector, whatever's in there. Check this out. This has the magnitude of a vector. Okay. This has the magnitude of a vector. Do you guys see it? Right there. And then it has the cosine of an angle right there. So if I let this fill in this gap, then this represents the dot product of the inside vectors, which means right here, these are the inside vectors. So this is equal to A, that's a horrible A dot, so that's the first vector, right? That's in there. A dot, what's the second vector? B cross C, because B cross C gives us a vector. Volume is that. It's pretty neat. Remember all those things where we did like a cross product and then a dot product on it and did the homework on that? Like, where am I ever going to use this stuff? Right here. Right here. This says, yeah, you oftentimes have dot products with cross products. Why? Because that represents the volume of a parallelepiped. Isn't that pretty cool? It's pretty neat. There's one more thing that we do. Sorry, I know it's dry. It's a long day. All right, stick with me though. We do this. That's not a magnitude because it's already a scalar. It's not a magnitude. It's absolute value. Because sometimes we can get a negative, but you go, hey, can volume ever be negative? Nope. That's why I have the absolute value. Say volume is not negative in this case. Just happens if we have our cross product out of whack or something. Y'all still okay with what we're talking about? We're going to wrap it up. I want to do one example. Before I do that, yeah, I'm going to have to prove it. I'm going to do it. Do it. I really hope you like this. It takes me a lot of time to actually go through this thoroughly and do this. I could just give you the formula, but it sucks. I don't want to do that. So I hope you enjoy it, because we're going to take a little bit of time to prove this. But check this out. If you wanted to do A dot B cross C, you would do the B cross C first, because the only way that you can figure this, well, you could distribute it, but I would do the B cross C first. So I'm going to start with that. So what this would equal, what this is, we would get this whole IJK, B1, B2, B3, and all this stuff. And you know what? If you want to write it down, great. If you don't want to write it down, that's fine. You don't have to write it down. But what you need is the punchline on this, because I'm trying to make your lives easier. Okay, this is going to make your lives easier. Well, it's really cool. That's why I want to give it to you. And then whatever we get, we would dot it with A. Why? We know dot product is commutative, so we know we can switch around. So if I do the cross product and the dot product afterwards, that's fine. Same thing. So whatever I get out of this is the cross product. I'm going to dot it with A. You follow what I'm talking about? Check this out. This whole thing would give us but I'm going to write it this way. I minus, so this is this, and if I make a mistake on the notation, please stop me. I don't want to get all the way through this and have something wrong, all right? So this with our I. You guys okay with it? And then we would go, okay, all right, cover up the middle. with the j. That's what we'd get, yeah? But here's the interesting part. If you dot product this with A, what happens is all we would do is we would multiply, can we do something just kind of crazy here? Can we just call this number 1, number 2, and number 3? Would that be helpful for you so we don't get all screwed up on this? So what this is going to give us, this is it, but this would really just give us this. A number with I, some other number with j, some other number with k, and then I would dot this with a. But when you dot that with a, check out what happens. What happens when you take a vector dotted with another vector? Do you get a vector? What do you get? You get a scalar. In fact, what happens, I would take my first number and my first component, I would have number 1 times a1. I would have number 2 times a2 and number 3 times a3. That's what that dot, verify that's what that dot product would actually look like. A1 and put it here, A2 put it here, A3 put it here. I'd have no I's, no J's, no K's whatsoever. For real, are you guys okay with what I'm talking about? Here's the cool part. What would happen if instead of having I, J, and K, I just put A1 and A2 and A3? Do you see that A1 and A2 and A3 are simply taking the places of I and J and K? Do you guys see that? Then there's another way to do this. If you ever have a dot product with a cross product, the easier way to do it is that right there. Replace I, J, and K with A1, A2, and A3, and you save yourself the headache of a dot product at the very end. And you do it exactly the same way you do any other 3x3 matrix determinant. Isn't that kind of cool? Do you guys want to do an example now, or do you guys want to take a little break and then come back and do it? You guys really are not going to talk to me today, huh? Whatever. You've beat my head into submission. I don't care anymore. While it's fresh, let's just go ahead and do it. This right here?
Yes.
No, it's not a magnitude because it's not a vector. What's this thing going to give us? It doesn't have any i's, j's, or k's. So when I find the determinant of that matrix, I get just a number, and so I don't have to find the magnitude, but I do have to keep it positive because our volumes are positive. That's why this is absolute value here, and we don't need that magnitude. Does that make sense? Let's try one. So I'm going to give you, how many points do I need here? 3. 1 more. I needed 3 points for 2 vectors, because I have originating point, endpoint. I have originating point, endpoint. How many do I need for 1, 2, 3 vectors? How many points? Need 4. Because I'd have 1, 2, 3, and 4. Do you guys get it? So I'm going to give you 4 points. We're going to find the volume of the parallelepiped, and then we're going to call it good. I'll talk about one more question, and then we'll take our little break, because we need it. That's parallelepiped. Find volume of BP. Find volume of parallelepiped when here's your points. By the way, some of you were giving me death looks when I was doing this, and you're like, oh my gosh, Leonard, I hate you so much right now. You're gonna love me. Love me. Love me. You're gonna love me when we do this problem. Trust me. This is gonna be a test question. It's gonna be the easiest one. Unless you mess it all up. Alright, it's not messed up. It's gonna be the easiest one because of what I just showed you right there. Trust me. Trust the Leonard. It's gonna be nice. You ready for it? Do you have it written down? Firstly, what are we looking for? Volume, area, what is it? And I give you these 4 points. What we're drawing is this picture. Do we actually have to draw it? Thank goodness, no. We don't have to draw it. But we do have to know what this is based on. Is this based on points or is this based on vectors? What is it? This is points. I want vectors. Can you give me vectors from my points?
Yes.
That's a big part of the class. Find me vectors from my points right now. It's going to be really easy if you start with what letter?
P.
Please start with P, because it's 0, 0, 0. You'll be subtracting 0. But go through and find me the vectors. You're starting with P every single time also. So I want PQ, I want PR, and I want PS. If it helps you to define these as like vector A, vector B, and vector C, that's fine too. It really doesn't matter, but if it helps you, then do it. I really hope you had an easy time doing that. Praying, man. Please let them get at least this, please. Please. Why is it so easy?
P is all 0.
P is the origin, and we know position vectors start at the origin automatically and the end at the terminal points. But I've left the notation free. What notations do I have here and here? Parentheses or those little brackets?
Brackets.
Because now they're vectors, now they were. Okay, so you're on your homework, you're doing some of these problems, you come across this, you go, man, I don't know how to find the volume of a parallelepiped. There's a formula for it, you get to have it, that's fine. How you find the volume of a parallelepiped, why we did all of this work, because it was a lot of work, is you get down to right here, and you go, okay, the volume is A dot B cross C. And if we get a negative, then we're going to change it to a positive, okay? Because it does have absolute value around it. I'm not putting it because I don't want to confuse you with magnitude. It's already a scalar. You can't even find magnitude. But it does have the absolute value. Nod your head that you heard me. You understand what I'm talking about. And you go, man, that's nasty. You got to find a cross product, then a dot product. And they go, wait a minute. We burned 20 minutes of class so that we go over here and go, a dot product on a cross product simply replaces this vector, this unit vector, this coordinate vector, we'll call it, the I, the J, the K. It replaces this vector with this vector. Just slide this one right over. And that's exactly what we've done. So literally all we have to do, follow the clip carefully, okay? All we've got to do is go, okay, hey, what's A? What's the vector A that we have up here? Put that. What's the vector B? Okay, what's the vector B? What's the vector C? And find the determinant of that thing. That saves you the dot product. Head down if you're seeing where those numbers are coming from. I really do need to know. Are you guys for real okay on it? Now, how you do it, don't let it confuse you. Where's the I? Where's the J? You're not getting a vector anymore, are you? You're getting a number. So just replace what you would normally do with the I, J, and K with these numbers right here, the 3, the -2, and the 1. So we go, okay, well, then this would be covered up. We have 8 minus 2, which is what?
6.
Times, normally it would be I. Not that sort of I. But now, because it's not I, it's 3. Hey, That's it. What's the next sign that we put?
Minus.
Cover that one up. I've got 4 minus 2. How much is that?
2.
But then I'm going to be multiplying by, be careful in sign, multiplying by,
Negative
I've got 1 minus 2, that's negative 1, and I'm multiplying by 1. Can you do that? Can you guys do that? Are you guys seeing where the numbers come from? Do you see how we do determinant 3, determinant negative 2, make sure the minus is there, then determinant times 1. How much does all that stuff give you? I got 18 plus 4 minus 1. 21. I'm going to ask you maybe a loaded question. Is this easy, medium, or hard for you? The actual doing it. Is it okay? Can you do it?
Yeah.
The understanding of this stuff, man, I gotta be honest, there's a lot that we have done in this class to get to this point. This formula is not that bad. I mean, it's just it's the determinant. But we have covered an awful lot of stuff. I want to talk about just a couple of those things right now, and then we're gonna take our break. Okay? The things you need to absolutely know in this class at this point are this: you need to know how to find a dot product. You need to know how to find a cross product. You need to know how to find the angle between two vectors. How to find the position vector of practically anything. You also need to know how to do some application stuff. If I give you two vectors, you should be able to find the area of the triangle that those things create. If I give you any 3 vectors, you should be able to find the volume of the parallelepiped that those things create. That's where you should be at this point. Do you feel like you're there? And the unit vector. Goodness, you got to find a unit vector. Can you do that? Okay. We're going to take a pause, and then we'll come back and do a couple other things. All right. I told you during the break I was going to ask you a question. I want to hear you think. There you go. Here's your question. What happens if you do all of this work? By the way, do you guys like this? Instead of doing cross product and the dot, it's pretty nice. Works only in the situation though. So if you have a dot on a cross, do that. But what happens if you do all this stuff and you get down to the very end and you get goose egg? What does that mean? You did do something right. You did something okay, but you're sure you're right. Double check, triple check, and you had your 4 points that were given, and you got 0. Can a parallelepiped have a volume of 0?
Yeah. Or wouldn't it just be area?
How?
It'd be a plane.
It would be a plane, which means that its height would be
0.
okay, which means what? If you have 4 points and you do this thing where you make this and you got the volume is 0, which means the height is 0. What's it tell you about those 4 points? They can't be equal, okay? They're obviously different points. They're
Coplanar.
If you have a volume of 0, it means that you have no height, which means that that point that's not in the other 3 points plane is in that plane. If your height is 0, it means the 4th point is in the same plane as the other 3 points. Isn't that kind of cool? It means you have something that's coplanar. So, if you ever have the situation if you ever have this situation where you have cross product, dot product, and it equals 0, here's what it tells you. It tells you that these 3 vectors, obviously they have the points, right? They have all this. These 3 vectors are coplanar. These vectors are, or all 4 points, either way, these are coplanar. In fact, that's how you test whether vectors are coplanar. You try to find the volume, guys. If you try to find the volume and it's 0, it tells you they're coplanar. If you try to find the volume that's not 0, it tells you they're not coplanar, and then you automatically get the volume for free. Does that make sense to you? So this is how you test whether these three vectors are coplanar or not. If this happens, A, B, and C as vectors are coplanar from the same length. It's kind of neat. Kind of neat. Now we're going to go back a little bit. I'm going to prove that one thing that I said I was hopefully going to forget about, and I didn't. So you're welcome for that one. We're going to prove that when you do a cross product, what you get is actually mutually orthogonal. We're going to talk about that. So here's what I've told you. What I've told you is that A cross B is perpendicular to A, and it's perpendicular to B. What we're going to do right now, I'm only going to prove one case of this. I'm going to prove that A cross B is perpendicular to A, and you can use the same method to show B, and then you can do B cross A with A and B cross B with B. It's a 4-case scenario. Does that make sense to you? Are you guys alive?
Yeah.
Okay, so we're going to do just one case, and you can extrapolate from there. So let's start proving that this is perpendicular to this. Here's what we know. So by the way, if you're looking for the proof of cross product does mean orthogonal, this is it. Okay, this is the proof I was talking about. Let's start with this. We talked about it. Oh, I should know it's going to be there when I ask you. You're going to yell it at me. I'm going to scream for joy. I'm like, woo! How do you check whether two vectors are orthogonal?
It's like dot product.
Dot product. Woo! I told you, scream for joy. That's my joy face. All right. So, hey, is that a vector?
Yes.
Is that a vector?
Yes.
If they are orthogonal, if they're orthogonal, then that has to be the case. That's got to be true. I just thought of a new way to prove this. Can we try it? Oh, this is going to be fun. This is going to be super fun. I'm so glad we did it after this, because just thought of it right now. For real, like for real. I'm not even lying. I usually lie about stuff like that, but I seriously just thought of it right now. Yeah, we're same. That's going to be awesome. That's got to work, right? It looks a whole lot like what we did, doesn't it? Like a whole lot. I'm just going to reverse them. Going unscripted right now. See if I hope it works. If not, I'll just edit it. You know, just press a button. I need my editor to freaking work. That's what I needed to do. Stupid editor. Anyhow, let's put it up here. What? Oh, you know, because we did. What would go on the top row? Would I have I's, J's, and K's?
No.
It's a little weird. We're doing the same thing though. We're saying A, B, C. Here's A, B, C. Now we're going, that's from here, A, B, C. Now we're going A, B. You guys okay with it? Same thing because we're the same two vectors, and then B's the only odd man out. Follow what I'm talking about? Why don't you guys see if you can work through this as I'm working through it, and we'll see if we get the same thing, okay? So let's do our cover-up. This is our last chance to practice the cross product in this class, really. It is as it applies just to doing cross product. We'll of course use it, but this is our last chance to do it in the section. So go ahead and practice. want to double check. Got it. Got it. Got it. Did you get the same thing I got? I want to be all super cool. Let's distribute this stuff. I want to distribute A1, A2, watch your sign, and A3. I want to distribute that. I want to see what happens. That's what I got when I distributed. Did you get the same thing that I got when you distributed? Do you see the magic? What happens to all of this stuff?
Yeah, cancel.
I love that. That's my favorite part of math, by the way. I love crossing stuff out. That's why I became a math teacher. I just like crossing stuff out. I couldn't really be the Terminator, but I could still, whatever. Terminator. What's it equal?
0.
That's a proof. I just proved that the dot product is 0. If a dot product is 0, then your vectors are perpendicular. They are orthogonal. If you replace this with B, same stuff. If you switch it around, same stuff. Replace it with B again, same stuff. It's always going to work out to 0. And that proves for you that when you're actually doing the cross product, you are finding a vector that is orthogonal to both A and B, the vectors from where you got that cross product. That's a proof for you. Show of hands if you feel okay with that proof. One of the easier ones we get to do. That's kind of nice. We're going to go one more step. We're going to talk about something really cool, really useful for you physicsy people. So let's talk about this thing. You know what we had? Tell me in your own words how you would describe that to somebody. What I've written on the board. We're at that point. I know you just learned it today. But how would you describe what that represents to somebody who had no idea what it was? I'm going to wait for you to say something. I can wait all day.
The length of a vector.
I get time. It's a length of a vector. That's true, because it's a magnitude. What vector? Length of a vector that is what compared to, I just kind of proved it. It's a length of a vector that's what? To
A.
Okay, so if you had to show it with your hands, could you show it? So like if you're like, hey, here's A and here's B, then A cross B is this way, and it's the length of that vector. That's what's happening. You guys okay with what I'm talking about? If that's true, if that's the magnitude of the vector that's orthogonal to both A and B, then we can use that to represent torque. Because when you have this lever and you rotate it, what happens to a bolt or anything that's being twisted, even the right-hand rule, guys, when you twist something from here to here, my fifth favorite dance move, what? Right behind 1/x. Okay, so anyway, when you take something from here and twist it here, my right-hand rule says, here's my vector, it's closing this way, the torque is going to go clockwise, right in. If I do the other way, take it from here to here, untwist it. Right-hand rule says, I did it wrong, didn't I? Sorry. Right-hand rule says, I'm taking this vector and going this way. It's going to twist it this way in. That is torque. So the magnitude of that twist, the magnitude of the vector that's going in, so perpendicular to both A and B, the length of that is how much torque you actually get. That's how we represent torque. Now, naturally, it's kind of nice to represent torque as an angular movement, right? So we're going to choose to say, well, okay, this thing can represent torque. True statement. But since we oftentimes rotate around something, we like to do that, right? We like to rotate around a particular bolt or tighten something down. If you ever torqued your lug nuts on your car, you know that we're rotating, and all of a sudden the thing goes click, and you go, oh, that's enough, 100 foot-pounds or whatever you're doing. So it can't represent torque, but we're going to use this to do it. We're going to say that this, by what I proved in class, another use for it, that we proved earlier. Spent a lot of time doing it actually, but wait, if this we just said represents the magnitude of that mutually orthogonal vector, we call that torque. If that represents the torque and these are equal, then we can use this to represent the torque as well. So we get this definition for torque that does this, and if you've taken physics, you might have seen it, but this is where it comes from. It says if we have torque, now torque can be thought of as a vector also, but we're going to focus on the magnitude of the torque, what you're actually getting out of it, okay? How much you're torquing that bolt, what you're actually doing. So when we take that torque vector, okay, well, how can we think about torque? We can think about torque as this. The two vectors you're actually using, instead of A and B, we're going to use some like real words here. The first one is how far away you are from your point, right? That's called your lever arm, and we use R for a radius to represent that. So one vector is, hey, how far away you're actually pushing on that. So that's our R. It stands for a vector. So if we use a vector to represent that radius, how far away our lever arm, and we take the magnitude, now we literally have the length of our lever. Big enough lever and I can move the world, right? So the further away we are, with the equal amount of weight, the more torque we're applying. You can see it. The magnitude gets longer. Your torque is more. That's happening. That just happened. And then we go, okay, well, what else? What else is there? Well, at the end of that lever arm, you're going to be applying a force. You're going to be pulling on that lever. Well, that force has a vector, and the magnitude of that force is how much you're actually putting on that lever. And you're going to be rotating that. So if I take my lever and I put my force at the end of the lever, I'm going to get some sort of angular motion around a bolt or something real that's turning. So how much we turn that is how much torque we're actually getting. So the sweeping out of that angle, sine of that, times these two magnitudes, that's the magnitude of our torque. It's actually really easy to find. R, we say that's our lever. F is our force if you want definitions. Let me give you one just really quick example, and then we call it good on our section here. So there's our what's that stand for?
Lever.
So this is the wrench, right? So we have a bolt right here. We got our wrench. Now normally, if you're smart about it, you're going to turn the wrench from right here. Doesn't make any sense. Why? You shorten your effective lever. You shorten the magnitude of that. You're shortening your torque. You're working too hard. You're applying way more force than you need to get the same amount of torque. Which is why we push logically at the end of our lever. We go, oh, let's go way out here. Rah! I feel like a man. All right. Anyway, that's how I get down. I just torque my lug nuts on my truck. And we're going to be, applying some sort of a force. And you go, wait a minute, this doesn't quite look like our typical torque situation, because what we want is a cross product. What we want is this vector to be right there, and you go, well, that doesn't. I'm not going to turn it from right here, but by vector addition, by what we can actually do with these things, these are all movable. Think position vectors. So we go, let's just pretend that our force is right here, and then it really does sweep out an angle. Which way is it going? Which way is that bolt going to turn? Now, I know that logically all bolts are kind of clockwise turn, but if you put your hand out and put it on the lever so that your palm opens towards where it's going, we're moving it this way. Where's that bolt going? If this was our lever and our force is going this way, we'd be going out towards you. Does that make sense to you? So we're going to be going in towards the board. In fact, when we think about it, our torque is perpendicular to what we're actually doing. Our torque doesn't go this way. It goes into the board so that it's perpendicular. It's actually mutually perpendicular with that. That's where our torque's headed. It's right in there. If this is on the flat plane, it's going into the board at 90 degrees. You guys all right with the idea? Do you actually have to move it? Not really. You just have to understand that that's what's going on. Is that we're sweeping out an angle. It's moving into the board. That's the plan. Let's go ahead. Let's do one example. Again, we're focused on the magnitude, how much is actually happening, and we'll call it good on our section. So you got a hex head bolt. Got a pretty standard, open end wrench, and then we're pulling on this thing. Pulling this thing with 50 pounds. So we're putting some weight on it. And I'm guesstimating here, so we're going to be rough estimate. That's 60 degrees. So again, the way this works is, hey, do you know the magnitude of your, you need some magnitudes. Do you know the magnitude of the lever?
Yeah, yes.
What is it?
9 inches.
9 inches. Inches, that matters. What's the magnitude of your force? Notice I don't really care about the actual vector because we're talking about magnitudes here. And then, do you know the angle between them? How much we're going to sweep out is what we're talking about. What is that?
660.
So if we want to find the torque in this situation, we got 9 inches because that's the magnitude of our lever. We got 50 pounds because that's how much force we're putting on it. And it's at the end of our lever. So if your lever was actually longer, but you were not holding at the very end, you'd have to go to where you're actually holding that lever. So if you had a 1 foot wrench, but then you're at 9 inches, you've lost some of that energy, which, that's typically what happens, right? We don't go, oh, here's my wrench. Hang on, right there. You can't do that because you can't get enough on it. So you're grasping it, yeah. So you got to measure to where you're actually holding that wrench. Sine 60. All right. How much is that? A rough estimate. So you can just give it to me to the 10th. So I know sine 60 degrees is root 3 over 2, but just use the decimal approximation of that. If you would, multiply by 50, multiply by 9, and tell me what you got. It should be like 300 something. 389.7 what?
Pounds.
Not
Poundage.
foot pounds. inch-pounds. Could you change it to foot-pounds?
Yes.
How?
Yes, divided by 12.
Divide by 12. Yeah. 12 inches in a foot. Divide by 12, and you go, okay, well, yeah, you know what? My torque wrench is in foot-pounds. About 32.5 foot-pounds, which that should make sense, right? You're putting 50 pounds, but not at the end of a foot. It's something that's shorter than a foot. You're going to lose force on that. You're going to lose torque on that. Is what I'm talking about. So, show of hands, feel okay with what we've talked about? Does this example make sense? Sweet. Any comments, questions, like anything about it? The torque thing's pretty cool, right? Something compared to what we've done, maybe even a little bit easier, like to visualize. And that's what I like to do. I like to make sure you at least can see something that's visual about it.
Does that count the wrench, or is that you putting the pounds on?
That's how much torque is being applied to that bolt. So you are putting down 50 pounds. That's staying there. The wrench is 9 inches long, so that's staying there. But when we're sweeping out that angle, we've applied 32.5 foot-pounds of torque on that bolt.